Good morning, yes, students. In the previous lecture, we have discussed about nearly free electron theory. In that theory, we have considered one electron which is moving through the lattice points and it is little perturbed by the crystal lattice, that is due to the potential. Then we have discussed about the formation of energy band considering a small perturbation effect on moving electron from the crystal lattice or crystal potential. That means it is almost electron is act like a free electron near the outside the ion core, but it is a little perturbed inside the ion core. This is what we have considered, and using this consideration we have observed the formation of energy bands. But today's discussion is another theory, that is tight binding approximation. Here what we are considering is electrons are tightly bound to the nucleus. That means, as you consider, see, this is one identical atom. This is the electron under consideration. This is another identical atom. This is the electron. So these electrons are tightly bound to the nucleus. Okay. So when you brought these two atoms close together, we can observe the changes in the energy of the electrons, because two electrons will interact with each other. So we have to consider, if you consider xi1 is the wave function of this, xi2 is this. When you brought close together, we cannot speak about this, so separate wave functions. So we are considering the wave function as xi. What is this xi? How you can calculate the xi? Xi is nothing but it is the linear combination of wave function of n number of electrons present in the given sample, right? So you can write this one as xi n. N varies from 0 to, right, n minus 1. There are n number of atoms. So this is, therefore we are calling this one as the linear combination of atomic orbitals. So in order to speak about the motion of electrons, we are considering the orbiting electron around the nucleus. So when n number of such orbiting electrons are considered, then net wave function is the linear combination of these atomic orbital wave functions of atomic orbiting electrons. So here, when you consider, to understand this, let us consider two-dimensional crystal lattice. See, in this diagram, these dots indicates the lattice points, that is, each dot corresponds to one atom, right? So therefore I am considering an nth atom which is at a distance of O from a reference atom. Similarly, consider an electron. It is an orbiting electron which is at a distance of r from O. That means what? This electron is present at a distance of r minus rn. It is a triangle of vector addition you have to do, right? Two vectors are taken in the same order, then resultant is taken in the opposite order, right? So, therefore, here in this theory, what we are considering is, see, the effect of potential on this p electron is not due to all the remaining n minus 1 electrons present in the sample. But what is this? This electron is affected by only the near or neighboring atoms only. That is important one. That means the electrons or the atoms which are present farther away to this electron contributes nothing. Only the contribution we are considering the electrons belongs to an atom which is present in the neighborhood of this. That is nearest neighbor only you have to consider. Rest of them should be ignored. See, this is the diagram just to represent here the crystal potential and electron potential, right? So what is the meaning of this? As you brought close together atoms, so the potential is started to becomes more and more negative. When the potential is negative means they are under more influence from the nucleus of the atom. Therefore here the potential becomes more negative means they are under tightly bound to the nucleus. To represent that we are using this. So, as I already told, let us consider an electron. Okay. The wave function of this electron is only influenced by nearest atom and is unaffected by the other atoms present in the lattice. So therefore, for this free electron, how we can write the wave function? See, for one electron, you can write, say, as you know, the wave function can be represented as usual, xi is equal to xi naught into e to the power ikr or minus ikr, right? You know, we are using the same situation here also. See, that is nothing but e to the power I k into Rn. So because we are considering an atom which is at a distance of Rn from O into xi naught, right? Into xi naught of R minus Rn. So that means we are considering an electron which is present at a distance of R minus Rn from the nth atom. Okay. So this is considering the one electron under consideration. If you consider n such electrons, what should be the wave function? That is what I considered linear combination of atomic orbitals, right? LCAO. So if you use that one, I can write the crystal wave function xi k of R is equal to sigma, right? Summation of all that. So now what we have to do? Next thing is we have to check whether xi k of R is satisfies the Bloch function or not, because electrons are moving in the periodic potential. Therefore, we have to check whether if the electron is moving in the periodic potential, it should satisfy Bloch theorem. Let us check it whether it is satisfies or not. That means let us calculate the wave function at a distance r plus rm. Okay. So that means what? R plus rm. When you move a distance is equal to rm, whether you are getting the same value xi k of r. Okay. So xi k of r plus rm is equal to, right, sigma n e to the power I k into rm, right? Xi naught of, in the place of r, what you have? R plus rm, right? R plus rm minus rm, right? So now this is equal to, I am multiplying with e to the power I k into rm. Okay. To balance this, what I am doing is e to the power I k into rn minus rm, right? E to the power minus I k into rm into e to the power plus I k into rm. So e to the power 0. So equation get unaltered, right? So into xi naught of, see, I am writing this, r minus rm plus, sorry, minus you have taken, here it becomes rn minus rm, right? What is this? See, whenever you are considering to this, it is just in the form, if you recall the Bloch theorem, in which we have shown the proof that xi of x plus a is equal to what? Xi of x into e to the power I k a. So we have used, right? If the Bloch theorem is satisfied, this expression holds good. If you have forgotten, just turn back your notes and check this step. I am making use of the same concept here. Okay. See, if here x is there, you have xi of x, right? In the place of a, if a is there, e to the power I k a, right? Now you just check here. This is equal to e to the power I k into rm. Then what is this? See, in the place of x, what you have? This, right? See, just observe here. This, it is better here. When you observe this equation, r, here it is r. Here rn, here rn, right? So that means what? Just observe here rn minus rm. In the place of rn, here you have rn minus rm, right? Rm minus rn. Just that means what? If you consider this one as x, in the place of x, what you have? Rn minus rm. That means e to the power ikx, r minus x, r minus x. What is this? Xi k of r. That means summation e to the power ik rn minus rm into xi naught of r minus rn minus rm means it is nothing but xi k of r. See, that is what you have proved here in Bloch theorem, right? Xi of x plus a is equal to xi of x into e to the power I k a. So xi k of r plus rm is equal to this much. That means what? Bloch condition is satisfied. So therefore electrons is moving in the periodic potential and it satisfies the Bloch equation.